Well, in the last class, we had started discussing the characteristics of mixtures, and then we found out that in order to properly define mixture properties in terms of single phase, or rather the pure component properties, we had to propose a number of mixing rules and combining rules, whether we were using the cubic equation of state, the virial equation of state, or the compressibility factor charts. So, we had to propose a number of mixing rules which were which gave us the constants, characteristics of the mixture in terms of the pure component constants, and then we found out that in those particular this empirical laws, there were some interaction parameters which took into account the interaction between unlike molecules, and in order to express them in terms of the interactions between like molecules. Say for example, if there is a mixture constituting of component A and component B, we would like to express the interaction of component A to A and B in terms of the interactions between molecules of component A and the molecules of component B. So, in other words, we would like to express Aij in terms of Aii and Ajj, and this was possible by means of combining rules. So, we had devised a number of combining and mixing rules, and based on those we had tried to define the mixture properties in terms of the pure component properties. And then we found out that suppose we would like to define particularly fugacity of a component I in a mixture of say C number of components where I extends from 1 to C. Then in that case, and I had also explained why it is so very important to define the fugacity of component I in a mixture, because that is what decides the phase equilibrium conditions. Now, under that conditions, we had found out from the basic equation R T ln 0 to P V mixture minus R T by P d P. This was for the mixture case. Now, if I try to find out the fugacity of component I in the mixture, so therefore, what does it become? It becomes F I, which is actually the partial molar, the contribution of component I to the mixture product. So, normally for any, and this should be, I will be explaining all the terms, this should be 0 to P, and here it should be V I bar, where V I bar it is nothing but, I had already described, it was del V del N I at constant T P N J not equals to I, minus we are often tempted to write this down as minus R T by P I. We are tempted to write it in this particular form. Now, let us see what should be here and what should be here before we proceed. Now, from where did this term come? This term is actually V I bar 0. What does it mean? It means the partial molar volume of component I in the ideal gas mixture, a mixture of ideal gases. There, what is this V I bar 0? Now, what is this equals to? This should be equal to del V del N I, where this is for the ideal gas T P N J not equal to I, right. Now, what is the total volume of the mixture? Total volume is R T by P into N 1 plus N 2, say N ith component, it goes till N n component, right. Now, suppose I differentiate this with respect to component N I, what do I get? I get del V 0 del N I at constant, T is constant, P is constant, all other mole numbers are constant. So, therefore, what does it reduce to? I can just get this one differential term when I am differentiating it with respect to NIRT by P. For all other terms they cancel out. So, therefore, under that condition this reduces to RT by P. So, therefore, it is very important to remember that basically the term which I use here, it is the partial molar volume of any particular component I. In this case, this RT by P came because it was the volume of the total gas mixture in the ideal gas state, because it is important to remember that whenever I define fugacity, it is with respect to P equals to 0, where the gas behaves as an ideal gas. And therefore, it is important to remember that V for the molar volume for a pure gas or a single component gas, that is equal to RT by P under ideal gas state, right. In the same way, so I will just repeat it once more. In the same way, V for an V0 ideal gas, naturally 0 means ideal gas, that is equal to RT by P. Interestingly, suppose this same gas, it is in a mixture with other gases, where I have to define the partial molar volume. Just note the partial molar volume, since it is molar, it is small case. It refers to component I, subscript I. It refers to the ideal gas state, superscript 0. This is a partial molar volume, there is a bar. So, just remember, if unless you give all the notations, all the necessary details are provided in this particular nomenclature, if you miss any of them, then the notation becomes incomplete. So, therefore, I keep on emphasizing the importance of correct depiction of the different properties. Again, I repeat, the primary reason for this is that we are using, or rather we will be dealing with a host of different sets of properties. Just for your convenience, if I can write it down, total properties, that means properties for the entire mass or for the whole system, they are given in terms of capital M. Molar property, the corresponding molar property, it is nothing but the total property divided by the number of moles contained in that particular component, whether it is a mixture, whether it is a pure substance, whatever it is. This will be denoted by M. Next, we go for partial molar properties. These have meaning only when any component I, suppose the total properties for component I. So, I can write it down as Mi, this is Mi, this is Mi. Okay. Now, when this component I is dissolved in a solution with other components, then only the partial molar property comes into being, otherwise no. So, therefore, when it comes, what is this? This is the molar property, small case, molar property of what? I. Suppose it would have been in a phase alpha. Suppose I have two phases, each comprising of say n components of pure substance, say in phase alpha, n components of pure components in say phase beta. Then in that case, the partial molar property of component I in the alpha phase would have been shown in this particular form. Suppose if I had two phases, but at the moment, since we are dealing with just mixtures either in phase, say the vapor phase or in the liquid phase. So, for the time being, I am not mentioning this, but moment we are going to mention phases and components, please remember component is subscript, phase is superscript, and small case means molar, and bar means partial molar property, right. So, therefore, the partial molar property of component I in the ideal gas state, that is when suppose I assume that the gas mixture which I have is a mixture of ideal gases. For that particular case, I find for a mixture of ideal gases, this is also equals to RT by P. Very frequently we tend to confuse this, therefore, it is very important to remember. So, therefore, accordingly, what is the equation for finding out the fugacity? It is RT ln. The fugacity, how I am going to denote this fugacity, we are going to discuss. Normally, we feel that there should be a bar, but whether I would give a bar here or something else, that I will be discussing a little later. And this fugacity, it has to be expressed in terms of the fugacity of this particular component I in the ideal gas state. what is the fugacity of this particular component I in the ideal gas state? If this I would have remained as a pure component, then the fugacity would have been equal to the pressure in the ideal gas state. But when it is mixed with a large number of components, then it manifests itself as the partial pressure of component I in the gas phase. So, therefore, this gives us the fugacity of component I in any particular state other than the ideal gas state, and therefore, in order to find this out, what do I need? I need to integrate it from very low pressure under which this particular real gas behaves as an ideal gas, and the fugacity, it is the partial pressure from this state to the pressure P where we normally want it, and this is equals to V I bar minus V I bar 0, which is nothing but equal to R T by P dP. So, till this much we had defined in the last class. I have also noted this down here with the proper definition of the partial molar property. Now, when we go to find this, then what did we find? That in order to calculate fugacity, we need to know the partial molar volume of component I in the mixture, not only at the pressure of interest, but since it is inside the integral, we need to know this particular value or how this varies with pressure right from P equals to 0 to the pressure of interest. Right. So, we need to know the partial molar volume, and also what is the other thing we know, which I have already mentioned here, the partial molar volume. It is not only a function of, this will be a function of temperature that we can keep constant, the total pressure, and it will be a function of the mole numbers of all the components, or in other words, it is a function of composition. We had already seen in the last class that this is different for different compositions of the same set of components making up the mixture. And it is also important on the composition, it depends upon the nature of the molecule or molecules of component I. It is dependent upon the nature of the other molecules which are present. So, therefore, finding V I bar in terms of P over the entire integration from 0 to P, that is something very difficult. In any case, we had already discussed that even finding out a generalized equation of state even for a pure component over a large range of conditions comprising the two phases was anyhow difficult. And you have already got a flavor of the large variety and number of equations that we deal in order to describe the PVT behavior of gases. The tremendous number of equations which had come up, as I had already mentioned, was just because no one equation was found to be suitable for the entire range of conditions that we would be dealing. Right. So, therefore, in this particular case also it was quite difficult. So, naturally, what people then tried to do, people then tried to find out whether any particular simplified model can be used in order to calculate the partial molar fugacity of component I in the mixture. Before we go that, it is important for us to realize the unique position of the fugacity of component I in the mixture as distinguishing from the partial molar property of any other compound. For any other component. For any other component, what did we find? We found out that for that partial molar properties, they are additive in nature, or in other words, when I write the total property, it is nothing but equal to Ni Mi bar, where M is an extensive property, and in terms of molar property we can write Xi Mi bar, that we have already seen. Okay, we had tried to express it in terms of volume, enthalpy, entropy, everything. What about partial molar fugacity? Let us see how the fugacity of the mixture, in what way is it related to the fugacity of component I in the mixture. Does it obey? Do we have a relation like Fm equals to Xi, say Fi bar or something of component I in the mixture? Do we really have such a equation, or such a equation does not hold for Fm? let us, for everything that we do, we are going to start from the basics. This is very important because we have to start everywhere, everything that we do. This is the basic equation from which we are going to start. Why? Because moment you try to jump steps, you will find that with standard states etc., you are going to get completely confused, right. So, therefore, this is something very, very important, and so therefore, let us see what we can do about it. So, therefore, let us start from the very basic equation which is given by this particular form. Now, what is that equation? What is the basic defining equation? R T d ln F m, which is the fugacity of the total mixture, that is equal to V m dt, right. This one we know. What is V m equals to? Just if we can write it in this particular terms, V mixture is nothing but sigma x I V I bar, fine. So, instead of V m, can I not write it down as x I V I bar dp, fine. Or suppose for a gas mixture, suppose, because usually we will deal with gases and then we will come to liquids. In that particular case, R T d ln F m, normally again let me define that mole fractions. This is another definition which you need to know. Mole fractions in gas phase, they will be denoted by Y. Mole fractions in the liquid phase will be denoted by X, right. So, therefore, what do we find? That the relationship between dl and Fm with the partial molar volume is given in this particular form. Now, suppose I try to expand it, then what do I get? Say for the time being, just for simplicity, for two component system which is a gas phase mixture at constant temperature and pressure. If I elaborate that, what do I get? R T d ln F m, this is equals to y I V I V sorry y 1 V 1 bar dp plus y 2 V 2 bar dp. Agreed. Now, what is this y V 1 bar dp? Can you tell me? This V 1 bar dp, it was nothing but y 1 R T d ln F 1, agreed, which is the partial molar fugacity of component 1 in the mixture, plus y 2 R T d ln F 2. The R T, if they cancel out, what do we get? We get d ln F m is nothing but y 1 d ln F 1 plus y 2 d ln F 2. Now, we start integrating this. If we integrate this from, say, p equals to 0 where F m equals to p to the point of p of interest, where for p equals to 0 to the point of interest at p, definitely we will also be integrating these particular terms also. This will be in terms of y 1 p to some particular situation F 1, this will be y 2 p to say F 2. So, in that particular case, on integration, what do we get? We get ln F m by p equals to ln F 1 by y 1 p y 1 plus y 2 ln F 2 by y 2 p. Or in other words, for removing the ln terms, what do we get? We get F m by p, this is equal to F 1 by y 1 p whole to the power y 1, F 2 by y 2 p whole to the power y 2. Is it clear to you? So, therefore, what is the relationship between partial molar between the fugacity of the mixture and the partial molar fugacity of the individual components? It is in no way related to the way the any other partial molar property m is related like yi mi bar. So, this relation does not hold for the molar fugacity, and since it does not hold, it is very important to distinguish the partial molar fugacity from any other molar properties. So, what do we do for this? Just to keep on reminding us that the partial molar fugacity does not possess the properties of other partial molar properties, it is something different from them. How do? We do not denote this with a bar that we have been doing it, we denote this with a cap. It just a hat to mark that this is different from this. So, therefore, what we do for each partial molar fugacity, it is important that we denote them with a cap, while we are denoting the partial molar volumes with a bar. So, therefore, from this particular equation, what are the things that we see? We see from this equation that more or less the fugacity of component I in a mixture, it is something different from the fugacities of, or rather it is different from the other partial molar volumes, number 1. And also it is important to remember that the molar volume of component I in pure state is equal to the partial molar volume of component I in the mixture. So, with this finally what we have done, we have tried to define the partial molar fugacity in terms of PVT behavior of gases when the component I is in a mixture. And from there we have realized that since it is very difficult to find out the partial molar volume of component I in mixture, not only at the pressure of interest, but over the entire range of pressure from 0 to 2, from 0 to P. So, therefore, it was felt necessary to suggest or to devise a simpler way of trying to estimate the partial molar fugacity of component I when it is in a mixture. Now, how to go about this? What people found out was that we started with gaseous mixtures. In gaseous mixtures, what did we find? In gaseous mixtures, we observed that, again suppose I start writing for gaseous mixtures, what do I get? First let me generalize this, but so therefore, this Fm by P, it can be better written as not sigma, but product of over I equals to 1 to C Fi by Yip whole to the power Yi. This is something which is quite interesting and quite different. So, the next thing is, in order to find out, rather since it is very difficult to, or rather although it is an exact equation, but it is very difficult to find out Fi bar. So, we wanted to find out some other way by which we can find out Fi for the different phases, and then we can start solving the other phase equilibrium problems. Now, for that, what did we take up? We tried to find out something simplifying, something much more simpler. So, what is the simplest thing that comes to our mind? The simplest thing which comes to our mind is as I had mentioned, mixture of ideal gases. Now, therefore, we have already seen, suppose we are dealing with a mixture of ideal gases, then in that case, again suppose what do I find? This is nothing but equal to RT dln. Now, very confidently I will be putting a cap, and please do not forget the cap, because this shows the partial molar fugacity. Here I would like to mention once more that when I put a cap, this is partial molar fugacity of component I in mixture, and when I just mention Fi, it is the fugacity of component I in pure state. So, you will find in several textbooks they try to put a 0, a star and lot of things, but just to make matters simple, so I am not going to add up anything. When it is a partial molar property, it has a cap. When it is in the pure state, it has no cap, and therefore, the only thing which, and the subscript I, it denotes component I. right. So, for a mixture of ideal gases, what do we find? We find for a mixture of ideal gases, this is equal to V I bar minus R T by P, the standard equation from 0 to P. Now, when we are dealing with ideal gases, then we know this is V I 0, which is nothing but equal to R T by P. So, for a mixture of ideal gases, this term cancels out and we know F I equals to Y I P, right. But this is a very restrictive assumption, or rather it cannot be generalized very easily. Why? Because this assumes that there is no interaction between the molecules. Now, while this can be imagined or this can be accepted for gaseous mixtures, we would like to propose a generalized expression to calculate the partial molar fugacity in terms of your compositions or something for all types of solutions, be it liquid solutions, solid solutions, gaseous solutions, everything, right. So, therefore, using the idealization for the mixture of ideal gases will become too restrictive. Then what people tried to do, they tried to find out the situation for a ideal mixture of real gases. Whether this could be a slightly more generalized version while being quite simple. Now, generally we find that the ideal mixture of real gases are those which conform to the Amagat's law of additive volumes, right. So, in the next class we will be dealing with the Amagat's law of additive volumes and whether it gives us a much more simplified version of calculating the partial molar fugacity in terms of composition. We continue in the next class.